It seems like most people have checked in. If you haven't, please do that. Couple things I want to do today. I want to review what we did last week. So, reviewing what a sequence actually is, the different types of sequences, and a little bit of factorials. And then I want to review the homework, so W1 and W2. I'll probably be focused more on W2 than anything. Um, but if you have questions over W1, we can go over that maybe just a little bit later. All right, if you did struggle with W2, which a lot of people in the last class did too, chances are I will put this in tomorrow during one of my free periods. So just try and get it done before tomorrow morning. Um, Besides that, after we review a little bit, I want to go over summation notation or sigma notation. And then we'll do a couple of examples of that. I'll introduce the homework, and then you guys can get started on that. Um, yeah. As just kind of a maybe a little bit of motivation, um, I think someone said in our meeting today we have like 5 senior class days left, so just keep that in mind. You guys don't have too much longer of this, and we're gonna try to get into a little bit more interesting stuff here in the next few classes. All right, so maybe with like 2 or 3 classes left, we'll be doing some a little bit more fun stuff. Um, so just keep that in the back of your head. Okay. Uh, so back to last week, definition of a sequence. Uh, a sequence is any series of numbers, any order of numbers that have a specific pattern and can be ordered 1, 2, 3, 4, and so on. Okay, there are 2 different types of sequences. They're infinite and they're finite. Okay, an infinite sequence doesn't end, right? So you can go first term, second term, third term, but it does not stop. It keeps going on. And a finite sequence stops at some point. Okay, within sequences, right? So there's infinite and finite. There are also 2 different types. They're explicit and they're recursively defined. Okay, so explicit, which is mostly what W1 was over, every term has a specific equation, right? So you don't need previous terms in order to get the next one. If you know the pattern and you have an equation, you can find the 1000th term without knowing any of the others before it. A recursively defined sequence is a little bit different. A recursively defined sequence is a sequence in which every term is dependent on terms before it. So a great example of that is the Fibonacci sequence. Okay, that says that every term, right? So the k term is the sum of the 2 terms before it. Right? So the k term is the sum of k minus 2 term plus the k minus 1 term. Okay, and I get that can be confusing at times. Um, we'll go over a couple of examples of that. And then the last bit are factorials. All right. So a factorial is just multiplying every number up until a certain point together. Okay, so n factorial, that's every number up until n and including n multiplied together. And in order to make this maybe a little bit easier to think about numbers on a number line. Right, so if we have n plus 1 factorial, it's 1 times 2 times 3 all the way up until n minus 1 times n plus 1. And we'll do an example of that here in a couple minutes. But that's everything on your screen right now is what we've gone over. Um, so with that, I'll kind of set up a couple of IXL questions, and we can go over those. So just give me 2 seconds here. Okay, so I'm gonna skip kind of the first part of this and get up to about the 60s, which is where you should see on your screen. Um, and keep in mind that W2 is literally all about recursively defined sequences. Okay. Will we have a test over this? Yeah, in some way, shape, or form. All right. So in this example, we're given A1. Right, A1 is equal to just 1. A2, that's also 1. And then the rule for AN is summing the term before it and the term before that. Okay, so keep in mind, these subscripts just mean the number of the term. Okay, so this little 1, that just means the first term. This little 2, that just means the second term. This N, that just means the nth term. N minus 1 is the term before that, and N minus 2 is 2 terms before N. Okay, so the subscripts are normally where people kind of hesitate or get a little bit messed up, which is okay. But what we're trying to find here is the third term, the fourth term, and the fifth term. Okay, so really all you do is you substitute in this first case, 3. All right, so if we're trying to find the third term, we need to substitute 3 in everywhere we see an N. And then we can simplify just a little bit. Right, so the third term now is the sum of the second term and the first term, which we know, right? So the second term is 1, and the first term is also 1. Right, so A3 is just equal to 1 plus 1, which is 2. So I'm going to pause for a second. Are there any questions over how I got that? Where did I get the 3? I got the 3 because we're trying to find the third term. Right, so we're trying to find A3, A4, and A5. So I picked A3 first, and that's where the 3 came from. And then we do the same for the fourth term. So in order to find A4, we replace 4 everywhere we see an N, and that equation in white. Then we can simplify a little bit. So the fourth term is the sum of the third term and the second term. Again, which we know. So we knew the second term, and we just found the third term. So A3, that's back up here. That's 2. And A2 is right there. So the fourth term then is 2 plus 1, which is just equal to 3. Questions about how I got everything in blue? Okay, now we need to find the fifth term, and then we're done. All right, so the fifth term, again, we just replace n with 5. Simplify a little bit. So that's equal to 5. And I'm not expecting you to show all that work. As soon as you kind of get the concept, you don't have to show like simplifying your subscripts. That's fine. But I feel like having this on paper is helpful. Okay, so questions about how I got any of those numbers? How did you get 3 plus 2 on the green one you just did? Okay, 3, so A4, that's the fourth term. The fourth term is 3. So maybe if I color code it. And then the third term is 2. Okay, so that's just substituting in what we found already. So the fourth term here, that is 3. The third term here, that is 2. All right, so this example, again, this is in the 80s, so this is a little bit harder. And we're trying to find the second term, the third term, and the fourth term. Okay, given that the first term is 92, and the rule for the nth term is 3/4 times the term before it. Okay, so again, the same rule applies. We want A2, so we replace 2 everywhere we see an n. So we get 3/4 times A1, which is equal to 3/4 times 92. So then we multiply 3/4 by 92, and we'll get our answer. So when we do that, we get this. All right, then we find the third term. And then when we do that, we get 207 divided by 4. And I'll pause there. Are there any questions so far? And then we just do that one more time. All right, so I'll shortcut this just a little bit. So the fourth term is just 3/4. The term before it which is 621 over 16. Okay, questions over how I got any of that? All right, so this all kind of works the same way. Recursive sequences are just sequences that depend on terms before the term you're trying to find. Okay, so you have a specific rule, you're given one term, and you just carry out that specific rule over and over again. And that's kind of all it is. All right. If you have further questions on that, we can talk about them later. I do want to move on just a little bit, so we can get to this stuff. All right. And I do want to review one more thing before we go on, and that is factorials. All right. So if you recall, factorials are just multiplying every number up until the number you're given together. Okay. So n plus 2, if we look at all this on a number line, where we start at 1, we go up to n plus 1, n plus 2, n plus 3, and then n plus 4. Okay, so if we rewrite n plus 2 factorial, that's 1 times 2 times 3, all the way up until n plus 2. And then the same is true for n plus 4 factorial. So that's 1 times 2 times 3, all the way up until n plus 2. And then we have to keep going, 10 plus 3, and n plus 4. Okay, so all that is substituting in what we know given the definition of a factorial. So are there questions about that so far? And then from there, all we're doing is simplifying. Okay, so we're taking common factors out of the numerator and denominator. So in the numerator, it goes up to n plus 2. So 1 times 2 all the way up until n plus 2. Right, and those cancel with everything similar on the bottom. So then we're left with n plus 3 and n plus 4 in the denominator. Okay, and that's pretty much it. Obviously, I would expect you to FOIL that. But that's, again, just another example of a factorial, which will come in, it'll be useful coming up in the near future. All right, and I just wanted to note, factorials do follow the order of operations, and they're kind of in the tier with exponents. Okay, so parentheses always have to come first, but then after that, there's going to be exponents and factorials. Okay, so 2 times n factorial is very different than 2 times n and then that factorial. They're two very different numbers. Okay, and you don't need to like memorize this. Just know that parentheses do make a difference. Okay, that's why this n plus 2, right, that's not equal to n plus 2 factorial. Those are two very different things. So again, factorials do follow order of operations. Okay, and then on to newer stuff. Okay, and this is all about summation notation. And a sum, again, it is just adding things together. But when we're dealing with sequences and probabilities and later in calculus, we're summing things together in very, very large quantities. So it's useful to have notation for it in order to shorthand it. Okay, so this Greek letter, sigma, that is the basis of summation notation. Okay, so what this means, whenever you see this letter, that means to sum things together. All right, and then there are different pieces that we need to know. All right, so this I in red, that's called your index. And all this really is a variable. And it will always match up with the thing you see inside the sum. Okay, so that variable can be anything. You can see x, you can see k, sometimes it's n. It just depends. But that's going to match up with your variable on the inside. This number in pink, that is your lower limit. So think of this as like where you start. And then this top letter, this n, is your upper limit, which is where you end, or where you stop. And then the inside, that's just a sequence. Okay, so that'll be a rule of a sequence. And what this entire thing says is that we want to sum from I is equal to 1, so from the first term, all the way up until I is equal to n, so the nth term. So if we write that out, we get a1 plus a2 plus a3 plus a4, all the way up until our upper limit, an. Okay, so that's what a series really is. That's the definition of summation notation and what a sum is actually doing. Okay, so I want to pause there. We will go over an example that'll kind of clear this up a little bit. I realize looking at a bunch of variables and different things is kind of confusing. But are there any questions over what that actually means? All right. So for example, and this should clear up a lot of things that you're probably asking right now. We have this sum, and what this is saying is that we want to sum 3i, so our series, our sequence, from I is equal to 1 all the way up until I is equal to 5. So we want to do 3 times 1 plus 3 times 2 plus 3 times 3 all the way up. So everything that I just wrote out, that's what that sum is actually saying. It's just a shorthand version of it. So are there questions about that? So I want to go over a couple more examples, and then I'll show you what your homework is actually going to look like. So again, this is the same thing that we did in the last example. We want the sum of 1 plus k quantity squared from k is equal to 3 this time. So it doesn't always have to start at 1, all the way up until k is equal to 6. So if we rewrote that, we'd have 1 plus 3 squared plus 1 plus 4 squared all the way up until 6. And then we can start to simplify that. And when we simplify all that down, we get 126. Okay. Are there questions about this example? All right. So the next thing, I want to go over some properties of these sums. Like every new kind of function we do, they all have properties. And the great thing about these is that they show up a lot later on. So if you take calculus next year, which I will hope you do, these rules still apply, right? You will see very, very similar rules to these with integrals, with derivatives, with all that stuff. So these are really important, and they're constantly being used. Okay, so we're going to start with that first property. And wherever you see a C in any of these, that just means there's a constant. So like 3, 4, 5, just a number times something else. Okay, and our first property says if we take this sum of a constant from 1 to n, we just get that constant times however many times we're summing it. Okay, and the reason being is because there's no I here, so we don't ever see that index ever again. So if there was an I here, it'd be C times 1, C plus C times 2, plus C times 3, plus C times 4, all the way up until n. But because that's not here, it's kind of just multiplying by 1 a bunch of different times. Okay, so if we were to rewrite this, if we were to write what this actually means, we get C for the first term, plus another C for the second term, plus another C for the third, all the way up n times. So whenever we're adding a bunch of things, or whenever we're adding one thing over and over again, that's just the definition of multiplication. Okay, so we can rewrite that as C times the number of times we're adding it together, which is n, and that's why that works. Okay, I'm not going to require you these to know just yet. I will probably later on down the road, but this is good kind of forethought into what we're going to be doing a little bit later. All right. So what this first property says is just the sum of a constant is that constant times however many times you're summing it. So in this case, it's just n. All right, that's this second property. We are summing the constant times a sequence from 1 to n. What that is equal to is we can actually just take this constant and put it on the other side of the summation. All right, and the reason why, again, if we write what this stuff actually means, we would get C times the first term plus C times the second term plus C times the third term, all the way up until C times the nth term. So there's a common factor in each of those terms, so we can pull it out. And that factor is just C. Okay, so when we pull that out, we're left with all these terms added together. And then in the inside of that parentheses, that is the sum of just AI. And then that constant is on the outside. Okay, so that's why this works. And then that third property, so we have the sum of two sequences. So we have the sum of the sequence A and the sum of the sequence B. And we can actually split that up into two different sums. All right, and the reason being, again, if we rewrite what this actually means, we get A1 plus B1 plus A2 plus B2 plus A3 plus B3, and so on, up until AN plus BN. And if we rearrange that, which we can do with addition, we get the sequence A and then the sequence B. And then again, this is the sum of AI and then this is the sum of BI. And that's why that works. Okay, so those are just two small proofs. Again, you don't need to know those proofs, but you should start thinking about these properties and what they actually mean. Okay, so let's move on. I'll let you, if you need to catch up writing, you can. But while you do that, are there any questions over what you see on your screen? All right, and the next thing is to just strictly define what this series actually is, which we kind of already did. So I don't want to spend actually too much time on this, but what I do want you to get from this little bit is that there are two different types of series. There are finite series, which you've already seen. So this means that we're summing from some number to some other number of some sequence. Okay, so that's a finite sequence. Again, that's A1 plus A2 plus A3 all the way up until AN, but then it ends there. But there can also be infinite sequences, okay, which is this stuff down here, all right? And what that means is that we're summing this sequence up until some term, but then we're going to keep going, all right? When you see an infinite sequence, you will notice it immediately because the upper limit will be infinity. Okay, that's like your cue that this is an infinite sequence. And we'll worry about how to deal with those later, but for right now, you just need to know that there are two different types. There's finite and there's infinite. And infinite can be really, really easily, you can tell really easily what's infinite and what's finite. Okay. From there, I want to go over, we will skip this example for now, but I want to show you what your homework is actually going to look like. Okay, there are kind of two different types of problems that you'll see in your homework, which is W10. All right, two different types. And for the most part, you'll see these top two. And then once you get into like 80 or so, you'll see this bottom one, which is a little bit harder. But for these top two, it's going to ask two questions. Really, it's going to ask one, and then you have to answer the next one based off of that. Okay, so the first thing it's going to ask you is it finite or is it infinite? Okay, which should be really easy to tell, because if this upper limit is just a number and it's not infinity, then it's finite. And again, for this bottom one, this upper limit and this bottom limit are both a number, so it is finite. So if either one of those are infinite, then you have an infinite series. Okay, but for both of these, we have a finite series. And the next question it's going to ask is the number of terms it has. All right, and for this first one, it should be really easily, right? It should be really easy. So if we look at this on a number line, and we start at 1 and go to 63, if we just count all those numbers, there's 63 of them, which I get sounds really simple, but it's very helpful to think about this number line when we get to things like the second example. All right, so the number of terms in this first one, there's 63 of them. Now in this bottom one, we don't start at 1 anymore. We start at -1. So we have to scoot back our number line, and we have to add 2 more. And then we have to go to 73. All right, so from 1 to 73, there are 73 terms. But then we have to add the 0 term and the -1 term. So really, there are now 75 terms. So these two examples are, for the most part, most of the IXL. Again, I think it changes over at about 75. So I'll pause for a second. Are there any questions over those top two examples? All right, and then we get this bottom example. Okay, so it says write the series using sigma notation with the lower limit of n is equal to 1. All right, and the first step is to actually get that sigma notation right. All right, so it'll always be this sigma, and the lower limit that it gives you will always go down on bottom. So that's step one, is just to get that lower limit. The upper limit is how many terms there actually are. All right, so this -2, that's the first term. 1 is the second. 4 is the third. 7 is the fourth. And 10 is the fifth. Okay, and this number is always the top limit. Now, if the lower limit was 0, you would start at 0 instead of 1. If it was -3, you would start at -3 instead of 1, and then you would count up. Okay. And then we have to make the rule for the actual series. Now, if you notice, each of these is going up by 3. So when we add 3 a bunch of times, that by definition is multiplication. All right, so we're going to have some multiple of 3. And then we can kind of start to test this, right? So our first term should be -2. But if we plug in 1 into our rule already, we just get 3. So we have to change that in order to get to -2. So in order to get to -2 from 3, we have to subtract 5. And then that's equal to -2. And then we can check with another number. All right, so if we want the fourth term, and we follow that rule of 3n minus 5, that should be equal to 7. And if we do that, we get 12 minus 5, which is 7. Okay, so our entire answer is that sigma notation and then the rule for the actual series. Okay, and that part in blue, that can be really tricky, but you really have to think about it. You have to think about what's changing from term to term, and then try and put that into mathematical terms. Okay, which again can be hard, but it takes practice. Okay, so questions over anything you see on your screen right now? All right, so that's what I have for you today. Again, your homework is W10, and I'll leave this open for a minute or two, just in case you have any more general questions. After that, if there are none, I will end this and then start a meeting in Teams. Okay, so again, questions on more generally, you can go ahead and ask. Otherwise, I'll end this, and then I'll start a meeting. All right, so since there's no questions, I'll end this and then I'll start a meeting on Teams. So if you have questions, I will see you there.